Hi all, this is our second lecture on statistical computing and machine learning, and today we will continue reviewing the fundamentals of probability theory. So let's see what the topics to be covered today. We're going to review the basics of random variables, discuss about CDFs and PDFs and moments of random variables, introduce a number of standard distributions from the uniform, the Gaussian, the binomial, Bernoulli, Multinoulli, and Poisson distributions. And I'm going to finish with a brief discussion on what is called the empirical distribution. So the goals for today's lecture are to understand the definition of random variables and the definition of CDFs and PDFs, to learn about the definition of the moments of distribution and how to compute those moments, introduce and acquire a working knowledge of different fundamental distributions from the uniform to the empirical distribution. And then I want to give you today a little bit of flavor of what is called the maximum likelihood estimator for parameters of these distributions. This is a topic that is going to be repeated throughout the course, and I thought this is a good time to give you a taste of these MLE estimates. Alright, so the references are the same as in lecture 1, and again I recommend Chris Bishop's book that doesn't have much requirements beyond a very basic knowledge of probability theory, and chapter 2 will cover most of the topics that we will see in the lecture today. Alright, so let's define what we mean with random variables in some basic way. So we're going to introduce what's called the probability space, which is the space of all possible events, and also we're going to introduce a probability measure P to measure the probability of different events from the probability space omega. So notation first. The random variable is a mapping from the sample space to the real line. So we're only interested in real value random variables. And the notation we're going to use is little x to denote a realization of the random variable x for the event omega in capital Omega. So we need to define a probability measure now, and the probability distribution of capital X is going to be defined as follows. Let's take any subset of the real line. So for example, B can be the interval from -1 to 1 or something like that. So we define the probability of B to be the probability of all the events omega that through the function x are mapped to this region capital B of the real line. So you can see here in another notation, x minus 1 of B is basically the events that through the random variable x, through the transformation x, are mapped to the domain B of the real line. So effectively, using the probability of events that we have seen from lecture 1, we can define now the probability affiliated with random variables capital X. So with this probability distribution of x for these intervals B of the real line defined, we introduce the probability density to be P of little x with a subscript capital of X, such that when you integrate P of x in the domain B of the real line, you get the probability P of capital B. Okay, so this is the definition of the probability density, and that's all we need to actually allow us to do the calculations for the lecture today. Okay, so usually you notice the notation here is a little bit heavy, and I put little x to indicate realizations, capital X to indicate the random variable, but you know, if from the context of what you're writing down is clear, you can actually omit the capital X and just write P of x, and that's usually what you will see in my lectures and as well as in textbooks. All right, so let me plot a few of these things. if I can write down the probability of little x being in the interval a to b, this in terms of the PDF p of x is given by the integral from a to b of p of x dx, and this is equal to what I call the cumulative density function computed at b minus the cumulative density function computed at a. And what is this CDF? The CDF is the area under the PDF p of x from minus infinity to the location of interest. So if you take any particular location and you integrate all the area from minus infinity to that location, that gives you the CDF at the particular location. So the probability of x belonging to the interval a comma b is given by the difference of the CDF values at b minus the value at a. So the CDF, you can think of this as giving you the probability that x is less or equal to z using this particular definition. That's what the statement that you see on the bottom. So f of little x is the probability that capital X is less than x. Okay. If I can go back just as a reminder, don't forget, if you compute this integral for z going to infinity, obviously the integral has to give you 1, right, out of the normalization of this probability density. So don't forget that this is a constraint that we always use to indicate the normalization of the PDF. All right. A few basic things that most of you are already familiar. This is the definition of the expectation of x. This is the definition of the variance. And if you do the algebra, the variance comes to be the expectation of x squared minus the expectation of x squared. So here, I should put parentheses around the expectation of x, right? But, you know, just to put things in a compact way, this is the expectation of x, the whole thing squared. You can define the standard deviation to be the square root of the variance. And similarly to the expectation of x, right? If you take any function of x, and I call this function here t of x, you can define statistical moments of t of x as well. So the expectation of t of x is the same as with what we use for x, but here you have t of x. The same thing for the variance. And you can see here, I put the parentheses to make it clear that this square is on the expectation. And I'm also giving you the definitions of other moments, in particularly what is called the skewness of the distribution and the kurtosis. These are the moments defined by taking these powers of x minus the expectation of x. For k equal 3, you get the skewness. For k equal 4, you get the kurtosis. And you will see these calculations for these moments to be typical in many engineering applications, and I will use them less in this course because at the end of the day we will most probably concentrate in all aspects of a distribution rather than just using particular moments. Okay, so summary for the discrete case, this is the expectation of f of x. Okay, you sum for all possible values of x. For a continuous, the summation becomes an integral. And then at the end, I am giving you also the case of the definition of what's called the conditional expectation. So if we want to compute, let's say, if we have a function f of x and we want to compute the expectation of f of x condition on y, then the only thing that we need to change from the previous definition, instead of p of x, we need to use the conditional density p of x given y. And we will see later on how to compute the unconditional expectation of f using this conditional expectation of f. For now, let me just say these conditional expectations are very useful because often this calculation is easier than computing directly the expectation of f. Okay, and we will see this in applications in machine learning as we move forward in this course. All right, let me do one example just to remind you that when you compute the expectation of a random variable, that expectation is not necessarily a value that we should expect that random variable to take. Okay, so what I'm going to do is I'm going to take our sample space to be the interval -1 to 1, and I'm going to take the probability measure to be uniform. So the probability of any interval within this interval of -1 to 1 is really the size of that interval divided by 2, right? So if I have a uniform probability measure, the size of this interval is 2, so the measure has to be 1/2. So the probability of being in any interval I is the size of I divided by 2. All right, so let me do the following thing. I'm going to introduce two random variables artificially made just to make a case here. So in one of those random variables, every event omega is mapped to 1, okay? And for x2, if the event omega is less than 0, the value of x2 is 0, otherwise the value is 2. Okay, so what I'm going to do is I'm going to calculate the expectation of x1, and I'm going to calculate the expectation of x2 and see what values they are and how they relate with the values that these functions take, which here, as you can see, are 1, 2, and 0. So I'm not going to go through all the algebra. You can read the slides and follow the details, but if you, let's say, take the expectation of x1 of omega, the density here, it's you remember we work with a uniform distribution, is 1/2. So x1 is equal to 1. So what you get is 1/2 times 2. So you get the expectation of x1 to be equal to 1. Similarly, for the expectation of x2, remember x2 is 0 for omega less than 0. So our integral here will have to be from 0 to 1, all right? X2 is equal to 2, so the expectation of x2 comes to be equal to 1. So for x1, the expectation actually is the value that this random variable takes, so that's nice. That's maybe what someone will expect, but you notice that's not the case for x2. The expectation of x2 is equal to 1, and x2 does not take the value 1 for any omega. Okay, so conclusion, basically what this example was to demonstrate is not to always anticipate that the expectation of a random variable will be a value that that random variable takes. In this particular case of x2, we see that e of x2 is equal to 1, and it's not equal to 2 or is not equal to 0. Okay. Let's move on, and I'm going to introduce the uniform of the variable. Obviously, I already use it in some sense, so I'm going to take the uniform of the variable defined in the interval a of b, a comma b, and so there is a scaling factor here, 1 over b minus a, to be sure that when I integrate this from a to b, I get 1. And this function, I remind you, is the indicator function. This whole thing is equal to 1 when I'm in this interval, otherwise is equal to 0. Okay, if you want to compute the CDF, basically what you will have to do for different x's, you're going to have to integrate this. So I'm just going to give you the answers. If x is less than 0, obviously you get 0. If x is between 0 and 1, if you integrate this, you are going to get x. And if x is greater or equal to 1, you're going to get the value 1. Okay, so again, this is for the very specific case where a is equal to 0 and b is equal to 1. Okay, you can sort of look at these formulas and maybe at least try to remember the mean value of the uniform distribution in general and the variance. So the mean value is a plus b over 2, as you will expect. and this is a very useful formula to memorize, b minus a squared over 12, and this is the expectation of x squared, all right? And you can get the expectation of x squared using the variance and the expectation of x, or actually the other way around. Most often you will get this first and then you will compute the variance, but one way or another, this is the formula for the expectation of x squared. All right, something I want to remind you is, right, because the integral of p of x for any distribution over the whole domain has to be equal to 1 from the normalization condition. I don't want you to get the wrong impression that p of x is less than 1, because it is possible p of x to be greater than 1, and I'm giving you here a simple trivial example with a uniform distribution from 0 to 1/2. You notice the density is equal to 2, all right? Because when you try to integrate 2 over the interval from 0 to 1/2, you get 2 times 1/2, you will get 1. So you notice that the density can be greater than 1. Okay, let's move to another distribution. So this is our definition of the univariate Gaussian. So distribution x around the variable x, we say it's a Gaussian, and we denote it like this, where the parameters mu and sigma square is the mean and the variance, if the probability of capital X being less than or equal to little t is this integral. So the density basically for the univariate Gaussian is what you see in this. And again, that's something we're going to see infinite amount of times. So it is important that you do become very familiar with this formula, not only for the univariate case, but also for the multivariate case that we will visit in another lecture. Now, a question that somebody can ask you is this distribution normalized? I mean, you can say most probably yes, because there is this weird factor on the front, and most probably that factor has something to do with the normalization. So we're not going to bother with the algebra here on showing that every distribution we introduce is normalized, but on the other hand, I don't want to take things arbitrarily, and so you may want, the first time you read the slides, to spend some time and look at this particular slide, because I'm providing you a proof that this Gaussian distribution is normalized, and the proof actually is very simple. I am working with this, this expectation here that you see, and so what I'm doing is I define this to be I, all right? This integral, I define it to be I, and then I do a little trick to compute I square by doing double integration in x and y from minus infinity to infinity in both directions. And then somehow, if you transform the x and y coordinates to polar coordinates, and you change dx dy to r dr d theta, and you integrate in theta from 0 to 2 pi, and in r from 0 to infinity, it comes out that I square is 2 pi sigma square. So immediately you can see where this normalization factor came from. Okay, so again, you may want to spend 1 or 2 minutes to see this little calculation that verifies that the univariate Gaussian is normalized. All right, so this is again our Gaussian distribution, and someone can also ask, I mentioned before that this is the mean and this is the variance, and you say, why? From where is that coming? Well, you're going to have to prove it. And the only way to prove it is to actually compute the expectation of x. So you compute this integral, and similarly you can compute this integral of x squared under the Gaussian PDF. And if you do these integrals, the answers come to be mu and mu squared plus sigma squared, from which you can get that the variance is equal to sigma squared. Now, how do you get these integrals? Let me just give you a hint. The only thing you need is you need to make use of the following formulas that you see on the bottom that these formulas, you can find them in integration handbooks, or if you search on the web, you can locate these nice formulas, and they are very valuable in computing the various integrals under the Gaussian distribution. So literally, to compute these two integrals and show that the mean is mu and the variance sigma squared, you only need these integrals that you see on the bottom. Let me introduce another notation. So when you write the Gaussian distribution, right, so you say x follows a Gaussian distribution, and these are the mean and the variance. A lot of times, instead of the mean, instead of the variance, we use the inverse of the variance, and that is what is called a precision. And the reason often the precision is a more useful parameter for the Gaussian is because it makes various calculations computationally and analytically easier than if you use the variance directly. So you can see here the name precision comes from the fact, right, that if you have a Gaussian distribution that is very narrow, so if sigma is very small, lambda is very big, so the higher the lambda, the more narrow the distribution is, and that's why this name of precision comes about. Okay, so let me keep moving a little bit more fundamental things with the univariate Gaussian. So this is what is called the standard Gaussian with mean 0 and variance 1, and this is the CDF of the standard Gaussian. And you may want to keep a note that I denote the CDF with a capital Greek letter phi, and I remind you the CDF for all the distributions we use the letter f. So the CDF for the Gaussian with mean mu and variance sigma square looks like that. Okay. Often, and I think this is going to come on the slide that is going to follow, if you want to calculate the CDF of any Gaussian with mean mu and variance sigma square, you can actually use the tables of the CDF of the standard Gaussian, and with simple transformation you can actually compute the values of this f at any location x. I'm not going to spend time here to discuss it, but obviously this CDF of the standard Gaussian is very much related with the error function that some of you may have seen in engineering courses, like diffusion problems, heat transfer, heat conduction, things like that. That's where the error function comes. So this is the definition of the error function. So if you have tables of the error function, then you can actually calculate the CDF of any Gaussian, univariate Gaussian, by computing this normalized variable z, x minus mu over sigma, and then evaluating the error function. That will give you the values f. All right, so again, for a standard Gaussian, my notation for the CDF of the standard Gaussian is Greek letter phi of x. That's the cumulative distribution of the standard Gaussian. And this is a typical plot of how this CDF looks like, right? You remember you integrate from minus infinity to a given location x. So it goes from 0 all the way up to 1. And this is the explicit definition of the standard Gaussian. Remember, the standard Gaussian has a mean 0, so yeah, that's why you get a z squared there, and it has a variance 1, right? So that's why you only get a 2 there. And as I mentioned before, if you want to calculate the CDF of an arbitrary Gaussian at a given location x, what you can do is you can evaluate the CDF of the standard Gaussian at x minus mu over sigma. And again, where is that coming? Well, you remember the CDF is the probability that capital X is less than little x, all right? So that means this probability is the same as the probability of capital X minus mu over sigma being less than x minus mu over sigma, all right? and the random variable x, capital X minus mu over sigma, follows a standard Gaussian. So that gives you the CDF that you see here of a standard Gaussian. So you may want to do this calculation in case it doesn't look familiar to you. All right. There's nothing new on this slide. Again, it shows you the univariate Gaussian with mean mu and this central interval here of plus minus sigma. And the expectation is mu, the variance is sigma squared, and we will make use of those facts quite often, maybe every other slide, because at the end of the day, many of the calculations in machine learning, they utilize Gaussians. All right, so someone can ask, why do we see Gaussians so often in machine learning, right? What is the whole deal about these Gaussian distributions? First, let me say what the limitations of this univariate Gaussian is. So you notice has only one peak, right? So if you have something that has multiple peaks, so if the distribution is what we call a multimodal, a Gaussian will not be appropriate. You notice it's symmetric. So if you have an asymmetric distribution, certainly it cannot be a Gaussian, or if you have data that don't look to be symmetric effectively, you will not be able to fit them with a Gaussian. And then you notice that the tails of the distribution, the CDF, the PDF basically goes asymptotically to 0 and rather fast, right? So you can see this is e to the minus x squared. So if you have distributions that have fat tails, so if they go very slowly to 0 asymptotically, then those distributions cannot be represented as Gaussian. So, so if you have a distribution that it's skew, has fat tails or has multiple modes, you cannot use a Gaussian for that. So, but why is Gaussian a good distribution to spend lots of time talking about? Well, it's an easy distribution, and even though you notice has this exponential here, the calculations with the Gaussians can be very easy. If you take logs, this exponential will disappear, and we will see that algebra with the Gaussian distributions is almost always very simple. Also, you may want to, and we will see this in a coming lecture, the reason we use Gaussians often is because a lot of times various events can be appropriately represented with Gaussian distributions, but let me just mention one of those. A lot of times when you try to model noise in your model, you always take this model, for example, to be an additive Gaussian, okay? And the reason that that is appropriate has to do a lot with the central limit theorem that we're going to visit in detail in 1 or 2 lectures down the road. But let me just state it with simple words what it says. If you take samples, n arbitrary samples from any distribution, and you take their sum of those random variables from that arbitrary distribution, then that sum follows a Gaussian distribution. Okay, so again, if you take x1, x2, xn coming from some arbitrary distribution, so x1 plus x2 plus xn divided by n, it does follow a Gaussian distribution. So this is quite sort of an amazing result, very fundamental to anything in statistics and many other fields, okay? And that, in some sense, justifies in various cases the utilization of the Gaussian distribution. And the other thing that I'm going to mention, and it may not mean a lot right now, but from all the distributions that have the same mean and the same variance, the Gaussian distribution is the one that makes the least assumptions beyond that mean and variance. And it is a distribution that, as we will see later on, has what's called the maximum entropy. Okay? And so you can think of this in sort of simple words, that beyond fixing the mean and the variance, this Gaussian is as uncertain, if you like, as it is possible, and that implies that this quantity that we will revisit, the entropy, is maximum from all other distributions that have the same mean and the same variance. We will actually prove this in a forthcoming lecture, so if it doesn't make sense right now, please hold on and we will revisit it. All right. So again, our Gaussian distribution, and let me just say that some of the tasks that we will see in follow-up lectures, when I will do the maximum likelihood estimation, will be to compute what the mean and the variance or standard deviation of this distribution are. So if somebody gives you some samples from this Gaussian, one of the first tasks will be to fit a Gaussian, and the way you fit a Gaussian is by computing mu and sigma square. So we will see this estimation, but for right now, you just remember that there is a procedure that I'm going to demonstrate today for another distribution, not for the Gaussian, that's called maximum likelihood, that allows you from data, from samples, to compute the parameters of this distribution. Okay? And so when you compute these parameters, you can also do fancy things. You can compute confidence regions on these parameters. You can compare, if you like, the values that you evaluate in the context of the samples that you got. But usually if somebody gives you data, and I'm going to demonstrate this with two examples, the way you're going to fit this data to a Gaussian is to compute from the data mu and sigma square with this so-called maximum likelihood estimator, and then plot the Gaussian for the evaluated mu and sigma square estimates. So let me give you two examples. This is a famous data set that's called normal data, and there is a link that hopefully it works in the slides. And so if we fit this data with a Gaussian, so if we compute the maximum likelihood estimator for mu and sigma square, this will be the Gaussian that corresponds to this given data set. So this data set has to do with larcenies between certain years, okay? And you can see how nicely this data fit with a Gaussian. A more interesting example is an example that the data come in the form of an image. So you can think here, every pixel in this image represents some intensities of electromagnetic radiation from photons over many years. Okay, and so what we would like is to take this data and try to fit a Gaussian. And so if you take all this pixelized data and you do again the maximum likelihood estimation that I will discuss it later on for the Gaussian, then you can fit a Gaussian, and you can see that Gaussian is a very nice fit to the histogram of the data that you see on the left hand side. Anyways, for those who are curious, because I postponed the discussion on the details for the maximum likelihood estimation of mu and sigma square for the Gaussian, let me just tell you that it comes out that the mean mu and the variance sigma square for the Gaussian that correspond to this maximum likelihood estimator are what we call the sample mean and the sample variance of the given data set. Okay, and again, if the word sample mean and sample variance don't mean anything, we will revisit those in one or two lectures. Okay, so let me so just remember that to these plots, the Gaussian, the way it is fitted is not just arbitrarily. We compute mu and sigma squared, and that's how the fit comes that you see in these plots. Okay, let me go to discuss a little bit about quantiles, and I'm going to do this for the Gaussian distribution, but obviously you can generalize this, and this is going to be very useful in many aspects of this course. So I remind you the CDF, compute at any point, is given with the integral of the PDF from minus infinity to that point. So let me define what is called the alpha quantile of a distribution that has a CDF capital F. So the alpha quantile is the location y of alpha. So I'm indicating this location with alpha, that's so I can call it an alpha quantile. So it's the location y of alpha where the CDF is equal to alpha. Okay, so again, the alpha quantile is that location in the real line. So for for real random variables, is that location where the CDF is equal to alpha. So if alpha, for example, is 0.5, you can think of y 0.5 being the location where on its left you have 50% of the probability mass, and on the right you have the other 50% of the probability mass. Okay, so that's the alpha quantile. Okay, so I can also define this tail area probability. So let me just put this schematic up. And I'm going to indicate the schematic for the standard Gaussian to start with. All right, so what you see here is the standard Gaussian, and I'm indicating two locations. One location that gives me a CDF to be alpha over 2, and here is another location that to its right it gives me a probability mass that is also alpha over 2. Now, obviously, from the fact that this area is alpha over 2 implies that this particular location here is the inverse of the CDF computed at alpha over 2. You remember the CDF at this point is alpha over 2, so this location then has to be the inverse of the CDF computed at alpha over 2. And similarly, this location, the area to the left of this location, right, is 1. The whole integral under the CDF is 1, minus this area here to the right, which is alpha over 2. So this location here, the CDF is 1 minus alpha over 2. So obviously I can evaluate this as the inverse of the CDF computed at 1 minus alpha over 2. Again, alpha over 2 are the areas under the PDF in the two tails. All right, so this area is alpha over 2 and this area is alpha over 2. So the area in between those two tails basically is 1 minus alpha. So you can actually use these calculations in the context of the standard Gaussian, but also you can extend them to any other Gaussian. So let me take a very standard example. When alpha is equal to 0.05 and define what's called the central interval 95%. Okay, so if alpha is 0.05, this area here is 0.025 and this area here is 0.025, so the area here is 0.95. Okay, so this is what we call the 95% central interval of the standard Gaussian. And if you go to the tables and you plug in alpha equals 0.05 and use tables of the CDF of a standard Gaussian, this point here comes to be minus 1.96 and this point here comes to be 1.96. Often we are using this as an approximation to be minus 2 and plus 2. So the 95% interval for the standard Gaussian is between minus 2 and plus 2 approximately, and you can actually generalize this to an arbitrary Gaussian with mean mu and variance sigma square, and show that the 95% central interval is approximately mu plus minus 2 sigma. Okay, so when you see people plotting mu plus 2 sigma intervals, this is the 95% central interval, and I'm demonstrating this here for a symmetric distribution, in particular for the Gaussian. Later on, we will define lots of other definitions of quantiles, especially for posterior distributions, but I think this is good enough for us to keep us going. So if you see this in your in a textbook or in a homework, you know exactly what that means. Okay, so let's move to some other random variables, and I'm going to start with the discrete setting. So I'm going to introduce a binary variable. So a binary variable can only take two values here, x equal 1 and x equals 0. So you can think this tossing a coin, and your variable is the outcome of the experiment, which can be heads, let's say x equal to 1, or can be tails, x equal to 0. And this distribution for these binary variables is defined by the probability that I get heads, that I call it mu, and obviously from normalization, the probability that x equal tails is 1 minus mu. So how does this distribution looks like if I want to write in a compact way? It looks like that, okay? If you wonder where this thing came from, notice that x can only take the values 1 and 0. So if it takes the value 1, this here, 1 minus x becomes 1 minus 1. So this becomes 1. So the only thing you get here is mu, which gives you this probability. And similarly, if x equal to 0, you get this probability. Now, a better way to remind yourself that the Bernoulli distribution is for a binary variable that only takes the values x equal 1 and x equal to 0 is to write it with indicator functions. And this is my favorite way of writing these binary variables. All right, so that way you really remember that this variable can only take the values x equal to 1 and x equal to 0, because otherwise these indicator functions that you see here will be 0, okay? And so when x equal to 1, this indicator function here is 1, and this gives you mu. When x equal to 0, this indicator function is 1, and you get 1 minus mu, which is what we started with. Okay, so what you see here, again, is a binary variable with two values. All right, so we're going to have to compute the mean and the variance for the Bernoulli distribution, and anybody can guess what the mean of the Bernoulli distribution will be. Remember, it takes only the values x equal to 1, so if you use this definition, right, it will take the value 1 when x is equal to 1, and that probability becomes mu, and then the value 0 with probability 1 minus mu. Then you do expect that the mean will come to be equal to mu, and the variance will be mu minus mu square. Now, from where did that come? You remember the variance is the expectation of x square, and x square also takes the value 1 and 0 with probabilities mu and 1 minus mu, so the expectation of x square is mu, and then you have minus the expectation of x, which is mu, square. That's how the mu square comes. I'm also giving you I mentioned earlier the concept of entropy. I am giving you just to have this formula coming with these slides under the Bernoulli distribution. I'm giving you the formula for what's called the entropy, and for now just take it as a definition, and in a forthcoming lecture when we discuss some basics of information theory, I'm going to elaborate a little bit more as to what this entropy means. But right now this entropy is minus the summation of all possible values of x of p log of p. And if you plug in the values x, 1, and 0, you get this nice result that you see in here. And some of you actually may recall that maybe they have seen this result in other courses as remote courses, as thermodynamics, for example, or statistical mechanics. All right, so that's the binary distribution. All right, so let me talk a little bit about, I mentioned before, the maximum likelihood estimated for the Gaussian. So let me start doing some calculations with the maximum likelihood to get you to the idea of what it is and how it works. And I'm going to do this for the Bernoulli distribution because it's very simple. So let's assume that we do this coin tossing experiment, right, heads or tail, and we throw the coin once, we get x1, so x1 can be 1 or 0. We get x2, which can come to be either 1 or 0, and we get xn. So this is my data set. I denote it like that, and I'm assuming here that this collection of the samples x1, x2, xn from this Bernoulli distribution are independent samples, and that goes with identically independently distributed data set. All right, so you will see this IID written in many slides. So let's say you collect this data, and after you finish tossing this coin n times, you collect m heads, and obviously the remaining n minus m will be tails. So the maximum likelihood is fitting basically this data to a Bernoulli distribution, which means computing what that mu is for the Bernoulli distribution. And the way we're going to do this, we're going to find the mu that the Bernoulli distribution corresponding to that mu best explains these data sets. And the best explains the data set is represented here with what we call the likelihood function, which is actually the probability of observing the data point x1, x2, xn, more compactly the probability of your data set for a given mu. And the reason this probability is decomposed as the product of x1, the product of the probability of x2, the probability of x3, etc., is coming from the independence of x1, x2, xn. And you remember, for independent events, the joint probability is the product of the marginal probabilities of x1, x2, xn, and this is what I have here. Okay? Now, each of this comes from a Bernoulli distribution. So xn is the outcome of the nth tossing of the coin. So xn can be 1 or 0, right? And you have the product of this for all tossings of the coin from n equal 1 to capital N. So when you do this multiplication, actually what you will get is you will get mu to x1 plus x2 plus x subscript capital N. And what is x1 plus x2 plus x subscript n is the number of heads, right? Because you remember from all of these x's, m of those you have heads, and n minus m you have tails. So the outcome here will be mu to the number of heads and 1 minus mu to n minus m. Okay. I am not going to do the optimization problem for the MLE estimate for the Bernoulli distribution, but let me tell you what you can do as a homework problem. All right. So you would like to find the mu that maximizes this likelihood. And because this likelihood has these powers here that make maybe the computation a little bit more difficult to some, what you can do, instead of maximizing this, you can actually maximize the log of this. And if you take derivatives with respect to mu and you set them equal to 0, you get the result that the MLE estimate of mu is m divided by capital N. So basically it turns out that the MLE estimate for this binary Bernoulli variable is the sample mean is. The sample mean, so effectively is how many times, what is the frequency of the times that you actually got heads, okay, is m divided by capital N. And we will see, I'm going to do this calculation in detail related to Bernoulli distribution later on, and that's why I omitted from the slides here. But we will see that in a lot of discrete distributions, the maximum likelihood estimator for the parameters is usually the expected values that you anticipate to get. And in this case, if you throw the coin 10 times and 8 times you get heads, obviously a good estimate for mu is 0.8, right? And this is what the MLE estimate is going to give you in this particular case. All right, so let me generalize a little bit the Bernoulli distribution. So in the Bernoulli distribution, what you did is you conduct this experiment with a coin only once. So how about if we have a coin and we're going to conduct this experiment n times, and we're going to concentrate in how many out of this n experiments, how many times we got heads. So for example, if n equal to 10, in 10 times, how many times we got heads? Well, the distribution that actually gives you that is what's called the binomial distribution. It basically it's defined as you see here, and it's distribution that tells you how many, the probability of getting m heads in n experiments, when the probability of getting heads in one experiment is mu, exactly like what we had before with the Bernoulli distribution. Okay, so in the binomial distribution, this term looks very similar to what we got in the Bernoulli distribution when we conducted n independent experiments, but here we conduct n experiments, and this factor on the front, for those who forgot, this is n factorial divided by m factorial divided by n minus m factorial. So this term here obviously is used to normalize the binomial distribution. So here is how the binomial distribution looks like for mu equal to 0.25 and n equal 10. Okay, and an interesting fact that I only put here for, let me go back. An interesting fact that I'm only using here for completeness is that when capital N goes to infinity and n times mu goes to lambda, this binomial distribution actually approaches what's called the Poisson distribution. We will see the Poisson distribution either in the lecture today or in a forthcoming lecture, but just remember there is a nice relation between the binomial distribution that is for discrete variables and the Poisson distribution that we will see later on in this course. Okay, I am plotting again the binomial distribution for mu 0.25 and mu equal to 0.9. So if you think about it, this corresponds to two coins that one of them has higher probability of giving you heads, all right? So this is an unfair coin, and this coin has a higher, probability of giving you tails, all right? So the different values of mu can be used to simulate these non-fair coins, and this may become to be handy when we do trivial examples later on in the context of Bayesian inference. Okay, now what is the mean? What's the variance of the binomial distribution, and is the binomial distribution with that factorial term on the front, is it really normalized? I told you it is, but sometimes it's good to start asking those questions the first time you see things. So the computing the mean and the variance of the binomial distribution is, you can use the definition, right, of the expectations and the variance, and do those calculations. But the simple calculation that I prefer to do in this slide is, well, to say, look, we're looking for the mean, let's say, of m, but m is x1 plus x2 plus xn, and each of these variables is a Bernoulli variable that has a mean mu. And there is a fact that you can actually use the basic definition of the expectation and the variance for independent events. So the statement says that the mean and the variance of independent of the sum of independent random variables is the sum of the mean and the variances of each of those random variables. So the expectation of m is the sum of the expectation of x1 and the expectation of x2 and the expectation of x1 of xn, and similarly the variance of m is the variance of xn and the variance of x2 and the variance of xn. The only thing that you need is the independence of these events. And actually, let me be a little bit more correct here. In the statement here, you don't really need the independence of events when it comes to computing the mean of m. So the mean of m is the mean of x1 plus the mean of xn, even if the events x1 to xn are not independent, but you do need the independence for the variance. So I am writing it in a compact way, the statement like that for both mean and variance, but remember, it is the variance where this independence is needed. All right, so we do know the mean of each of these variables, and we do know the variance of each of these variables. So actually, if you need the expectation of the variance is n times the mean of the Bernoulli, and the variance is n times the variance of the Bernoulli. So you don't really have to do this complex summation, which may take you a page or two to actually derive. You can use this trick, and there is the answer. There is another third way to actually compute this, and I am not going to do it. For those who want to challenge themselves, here is what the trick is, right? The equation that you see on the bottom is basically nothing else but the normalization condition for the Bernoulli distribution. So if you take derivatives of this with respect to mu, you will see when you take the first derivative, one of the terms is going to come to be this expectation. And if you take second derivatives, one of the terms is going to be this expectation, and that can give you those two results as well. Okay? Again, it's a trick. I am not going to elaborate, but effectively what you need is you need to use the normalization condition that you see on the bottom and take derivatives with respect to mu. I mean, this answer that I already gave you here is good enough, but here is another way that also is rapid in deriving this these moments for the binomial distribution. All right. So you remember when I mentioned for the Gaussian, I asked you why are you sure that the Gaussian is normalized? And obviously the same thing somebody can ask you here. Why is the binomial distribution normalized? So I am not going to do the derivation. It's given on this slide to prove that this normalization, that this is equal to 1. You need to use two facts, right? So the proof is really on the bottom, and you need to use two facts. One is this equation that you see on the top, that you can actually prove it by direct evaluation of these two sums. And then you have to use what's called the binomial theorem, which is 1 plus x to the power n is this summation of n over m to the power x m, okay? And if you use this plus the binomial theorem and some rewriting of the normalization condition, you immediately can see that you get a value of 1, okay? And I think I noticed before in the previous slide, most probably I don't want to go back, there was a typo in the summation here. So obviously when you sum, you have to sum for all possible values of m, and I think in the previous slide there was m equal to 1. So, you know, maybe in n experiments one of the outcomes can be 0 heads, so we need to include m equal to 0 here. So we will correct that in the posted slides. So the binomial distribution is normalized, and again, for those who want to see the proof, is given on this slide. So let me generalize now a little bit the Bernoulli distribution. So the Bernoulli distribution again is about binary variables that can only take the values 0 and 1. So now what I'm going to consider is discrete variables that can take capital K possible mutually exclusive values. So you can think, you know, a random variable that can take 5 possible values, but each of them is going to be 1 or 0, okay? So let's say, think of the random variable being a vector 5 by 1, okay? And possible outcomes for this random variable can be 1, 0, 0, 0, 0, or 0, 1, 0, 0, 0, or etc., 0, 0, 0, 0, 1. All right, so we have this vector x where only one of its values in one of the components is equal to 1 and everything else is equal to 0. And this vector is a vector that is capital K dimensional. So I have capital K states and only one of them is 1, the other one is 0. So you can think of this random variable having capital K states, and only one of those states is on, every other state is off. So obviously this is going to be very useful for many applications in machine learning. And the way that I define here with this hard coding where only one of the variables is 1 and the rest is 0, obviously I'm implying that if I sum all the possible values of this xk's here, right, xk is the value in the little location k. If I sum all of this, obviously I'm going to get 1 because only one of those xk's is equal to 1 and the rest is 0. So we need to introduce a probability distribution for this. To do so, let's define as mu k to be the probability that the little k value is going to be on. So this is going to be mu k. And I'm going to generalize my Bernoulli distribution, and I'm going to write my probability of x by this nice formula. And again, when I had before the Bernoulli distribution, you remember I had two terms here. I had mu to the indicator function of x equal to 1, and then I had 1 minus mu to the indicator function that x is equal to 0. Here I have the product of these terms for all possible values of k because I have capital K states. So for example, if let's say only x2 is equal to 1 for this particular x, then this whole product is going to give me just m2 and all the other terms are going to be equal to 1. Okay, so if you only set x2 equal to 1, this indicator function for k equal to 2 will be 1, so I get m2. For everything else it will be 0, and for those mu to the power 0 you get 1. Okay, now because these mu's are probabilities, they have to sum equal to 1, which sort of poses not a significant, but you know, something a little difficulty that we need to be concerned. You notice that this probability mu k's, they are not all independent of each other. So effectively even though I have mu1, mu2, mu capital K, only capital K minus 1 of these values are independent. One of them can be set as 1 minus the values of the other K minus 1 independent values. So this will be important when we do maximum likelihood estimation, which I'm going to do actually for this case, generalizing basically what I mentioned with words for the Bernoulli distribution. Okay, so I don't really have to tell you, but if you sum for all possible values of x, this distribution comes to be normalized already. And again, I recommend take capital K to be equal to 3, for example, and the possible values of x will be 1, 0, 0, 0, 1, 0, and 0, 0, 1. And when you compute for each of these cases this product, you're going to get mu1 plus mu2 plus mu3, which is equal to 1 by the constraint that I mentioned in the previous slide. So you can actually compute the mean and the variance for this distribution easily. And the easiest way to do this is to use actually the results from the Bernoulli distribution. So, if we're looking at vectors x, right? But in some ways, every component of this vector x is, it's a Bernoulli variable that it's either on or it's off. So you anticipate that the mean of x1 is going to be mu1. The mean of x2 is going to be mu2. So the mean of the vector x is going to come to be mu. And so I don't really need to derive anything. So this distribution is called the categorical distribution. And a more often name is the Multinoulli distribution. And the reason I call this the Multinoulli distribution, it's sort of, if you think Bernoulli distribution was for binary variables, so it would make sense to call this the Multinoulli. But in many textbooks, this is introduced as the categorical distribution. Now, this distribution is also related to what is called the multinomial distribution. And the multinomial distribution is basically the distribution where in n experiments I will get m1 times state 1, I'm going to get m2 times state 2, and m subscript capital K state K, okay? So the Multinoulli is generalization of this multinomial distribution, where actually I don't conduct n experiments. The way it's written here for the multinomial distribution, I only conduct one toss of this coin with k states, all right? And that's why you see here n equal to 1. But apart from that, the two distributions are very much related. I'm going to show you on the next slide how this multinomial distribution looks like. Okay, so before I do that, let me do this maximum likelihood estimation for this Multinoulli distribution. So we're gonna collect the data set. So we're gonna do the experiment n times, and notice this x1, x2, xn are vectors, right? Because each of them has capital K states. So the likelihood again will be the product of the individual probabilities that I get in each toss of the coin. That's this product of a little k. The product of a little n comes from the independence of this data. And if I pull this product outside and I push this product inside, I can write actually this product over this mu k's to the power x and k as mu k to the sum of x and k's for all n's. All right. So what is x and k? Is the value of the random variable for state k in my nth toss of the coin. All right, so x and k is either on or off, it's 1 or 0. So if I sum x and k for all n's, I am going to get how many times my n experiments this k state was on, and I call this m subscript k. All right, is how many times the little k state was on when I conducted n experiments. So you notice that when you calculate the likelihood like this, you don't anymore need this data. All right, so you can actually throw this data set D and the individual values of x1, x2, xn, you can throw them away, because in estimating the parameter mu of the distribution, the only thing that you need is these values mk. So once you have done the summation, you can actually throw the individual x's. So this m values is what they are called sufficient statistic, is the only information from the data that you need to compute mu. And this is a very essential, important concept that is going to come up all the time. All right. So again, the sufficient statistic is this function of the data. In this particular case, that function is just the summation that you see here, that itself is sufficient to define the likelihood, and thus provide us an MLE, a maximum likelihood estimator, for the mean mu of the distribution. Okay, so let's do the maximum likelihood. So what I'm going to do is I'm going to take this expression from the likelihood, and I'm going to try to maximize it. But before I do the maximization, I'm going to use the logs of this equation to make algebra easy. And the logs, you remember when you have products of different terms and you take logs, the product becomes a summation, and the logs of each of these terms is going to be m times log of mu. All right, so I'm going to do that. And this is what you get when you take the log of the likelihood. But somehow out of nowhere, I see another term here in my objective function, if you like. And that term is a Lagrange multiplier times the constraint that we had in our problem. So this is sort of an augmented maximum likelihood estimator, because it says, yes, maximize this, find me the mu that maximizes this log likelihood, but be sure these values that you compute are always summing equal to 1. A lambda is a Lagrange multiplier. So now what we need to do is we need to optimize this with respect to the parameters mu and with respect to the parameter lambda. And the way you're going to do is you're going to take derivatives with respect to mu, set them equal to 0, and derivatives with respect to lambda, set it equal to 0, and then solve them for mu and lambda. And the derivative with respect to lambda, obviously you can see is this constraint. All right, that's what lambda does. It enforces this constraint. The derivatives with respect to mu, you're going to have to take derivatives of the logs. And so when you do this algebra, the calculations are given on this slide, so I'm not going to go line by line. So if you take derivatives with respect to mu k, you get this equation, which is not of any use because it involves this unknown lambda. So what you can do is you can take this equation and put it inside the constraint, which is that the sum of all the mu k's has to be equal to 1. And then when you just do simple algebra, you can immediately see that lambda is minus the sum of the mk's, okay, of the sufficient statistics. And if you plug in this lambda inside this estimate of mu k, you get the expected answer that says mu k is mk divided by n. So the probability basically that the state k is on is the frequency that in my n observations that the state k was on, is the empirical mean, if you like. Mk over n is how many times I observe in my n experiments the state k to be on, and that's what it turns out to be the maximum likelihood estimator. Now you may say, couldn't we just state this directly without bothering about maximum likelihood, Lagrange multipliers and all of these things? Yes, we could, but this is the rigorous way of doing it. And unfortunately, in many other problems, we're not going to be getting simple answers as you see here, and the calculations for other distributions will be way much more involved than what you see in this particular case of the Multinoulli distribution. So again, for the Bernoulli distribution, I told you with words that the answer coming up was the same, and this is the generalization now for the Multinoulli distribution. Okay, I mentioned that I'm going to give you one slide on the multinomial distribution, so I'm only writing down the definition of the multinomial distribution. So that's the distribution that in n experiments I observe m1 times state 1 to be on, m2 times state 2 to be on, mk times state capital K to be on, and this is a normalization factor, and the meaning of mu1, mu2, mu k is exactly the same as before. All right, the summation of all these m's obviously has to be equal to the number of experiments, n, and again, I'm not going to give you a proof that this is properly normalized, but effectively you can see why the multinomial distribution generalizes the Multinoulli distribution for n equal to 1 that we saw in the previous slides. All right, let me finish with one experiment that involves an application of this Multinoulli distribution to biosequence analysis. So what I have here is I have different sequences of the DNA, and you can see I have 10 sequences. Each row here is a sequence of the DNA in 15 different locations along the genome, and these letters that you see here are basically the fundamental if you like chemical building blocks of the DNA. These are the letters A, C, G, and T, and you also notice that in a few locations in the genome, some of these chemical building blocks are the same, and these are important locations, and they indicate basically the locations in the DNA where we have what is called the coding region. These are locations that are being preserved by evolution. So this is, for example, location 7 that you notice is all this chemical block G. So how is this related with the Multinoulli distribution? Well, if you look at its location in the genome, so for example, if you look at the first location, you notice you have some C's, one T, one G, so you can think the Multinoulli distribution basically being a distribution that tells you how many times you get C, how many times you get T, and how many times you get G, and how many times you get A, right? So it's like having 4, if you like, states. And so what is often being done to plot this data, you look at its location and you plot these empirical means that we indicated 2 slides ago that correspond to the maximum likelihood estimator of the this Multinoulli distribution. And what you do is you plot this empirical means or MLE estimates by showing these letters in sizes that are proportional to the MLE estimates. So for example, if in one location you have more C's, what you will do is you will plot the letter C to be much bigger than the letters T and G in proportion to its frequency in the first location in the genome. Okay, and this plots this sequence logos, they look like that. Okay, so you can see in location 1 you had more of C, so that you plot it in proportion to the MLE estimate for C. In location G you only had G, so you can see a huge letter G, and this is again this type of a plot is called the motif, and is used to present biosequence analysis data in a graphical way, but really it's nothing else but plotting the MLE estimates in different locations in the genome. Okay, let me summarize with a table coming from Kevin Murphy's book that takes us from the Bernoulli to the binomial, and then from the Multinoulli to the multinomial, just as an explanation of this table, and you can study it more on your own. If little n here is equal to 1, this is rolling only once the dice. If n comes with this little dot, right, this corresponds to what I referred before, this capital N rolls of the dice that I had before. And capital K equal to 1 implies binary variables, and when you see these lines here, implies I have that I have 1 out of capital K encoding. Okay, and so this is basically a little bit of summary of the of all the discrete distributions that we would like to know more, so we can use them later on in our course. Okay, I just have a slide with the Poisson distribution, and for now, and I'm going to come back, I think, to this distribution to give you a little bit more details. It's a distribution that is used to model counts of different events, for example, counts of rare events, and it's defined by some parameter lambda. And you can look at the Wikipedia for the mean and the variance and the other bounds and more details of the Poisson distribution. But again, I'm going to come back to it later in the course, and you can see different plots of the Poisson distribution. And actually, when you look at this plot for lambda to be a very big value, you wonder, can the Poisson distribution be approximated with a Gaussian? And the answer is yes, it can. And we will briefly discuss this in 1 or 2 lectures from now. All right, so let me finish with something a little bit ahead of our the topics that we covered today, but a sort of a relevant type of idea that I want you to see, because it's going to be useful in the discussion of Monte Carlo methods. So consider the following, right? So, consider that we have a distribution P of x, and we sample from that distribution x1, x2, xn, so this is my data set. And somehow, we don't really, maybe we have a mechanism to take samples from P of x, maybe we have a computer code that allows us to take those samples, but we don't really have an exact analytical form of P of x. So the only thing we have right now is the samples x1, x2, xn. So if the only thing you have is the samples, a lot of times we approximate the distribution P of x with these samples, and the approximation is what is called the empirical distribution, and I'm going directly to this equation here in blue. So this is my definition of the empirical distribution, P empirical of x, and you can see what it is. It consists of delta functions that are these spikes at the different locations defined for each of the samples, x1, x2, xn, and each of the spikes is weighted equally by 1 over n. You can generalize as this equation in red shows, and you can make these weights anything else you want to, assuming that these weights are normalized. But right now, let's concentrate on this definition in the blue line of the empirical distribution, that are these spikes, x1, x2. And remember what these delta functions are, right? When you integrate them, you get 1, okay? So what good is that distribution? And I want you, obviously, I said that maybe it can be used to approximate P of X, all right? We don't yet have any measures on what does it mean to approximate a distribution, so we will see this later in the course. But right now, what I want to do is I want to finish the lecture today with the following fact. Suppose somebody tells you, I know you don't have P of X analytically, but I want you to find for me the expectation of some function of X, f of X. Can you at least come up with some sort of an approximation of the expectation of f of X? Well, because we don't have access to the actual distribution of P of X, we can approximate the expectation of f of X as the expectation under the empirical distribution. And I'm using here the definition of expectation, so I plug in my empirical distribution, and then I am pulling the summation outside, and then I have an integral of f of X multiplied with each of these delta functions. And for those who remember these things from calculus, when you multiply f of X with a delta function central location xi, and you integrate effectively from minus infinity to infinity, what you get is you get the value of the function f at xi. So this expectation of f of X under the empirical distribution comes to be 1 over n, the summation of f of xi at the sample locations. I should change the indices here, so I should put a little n, from little n equal to 1 to capital N. Okay? And this is what we define to be the empirical mean of f of X. So the empirical mean comes actually to be an approximation to the actual mean of f of X, where the approximation involves using the empirical distribution rather than P of X that we don't have access directly. Okay, so again, I'm throwing this idea of the empirical distribution early on, and we will come back to say many more things about the empirical distribution and its significance. But right now, we notice that this result of the sample mean that maybe you know from your undergraduate courses comes to actually be nothing else but the expectation of f of X under this empirical distribution, and we take this as an approximation of the true expectation. All right, so let me finish there, and we will continue next Tuesday with another lecture for our course. Thank you, bye.